So, good morning, everyone. So, today we are going to learn one of the most important theorems in fluid mechanics. So, let me just start by asking you a simple question. Why does an aeroplane fly? Why does perfume come out of an atomizer? And why can a strong cyclone sometimes blow away the roof of a house? Have you ever thought about that? These all look like completely different phenomena, but all of them can be explained by one simple principle or theorem of fluid mechanics, that is Bernoulli's theorem, which we are going to study today. So let's look at the physics behind it. Okay, we'll not just only uh, understand the formula, we'll also understand the physics behind it. Okay, so let's suppose we consider this is a fluid element, this is a small fluid element, and of a flowing fluid. Suppose we consider that this is a flowing fluid, and fluid is flowing like this, like this, like this. So we cut out a portion of it. Okay, we cut out a portion of it and we draw it like this. Okay, so we consider a fluid element, and within that fluid element we consider a very small mass of fluid. We take it as dm, since it's a very small mass, and we consider the volume to be dv. So whenever I write v like this, it's volume. Okay, and whenever I write a simple v, it's velocity. Now I hope I'm clear with that. Yeah, so we consider a very small element, dm, which has a volume of dv, and it has a velocity of v. Simple. Yeah, and suppose we consider a baseline here, and suppose this is the center of mass of this fluid element. So this height we are considering as h. Okay, so here the potential energy will be zero. You already know about potential energy. So since it's at a height, so here potential energy will be different. And one more thing, I can write here dm is equal to rho. Rho is the density of the fluid, and dv. So this we need to keep in mind. Okay. Now let's go back to what are the different types of energy in a flowing fluid. So this is a fluid which is flowing, right? This is the fluid which is flowing. So it has different kinds of energy in it. What is the one most common energy that we can have? Since it has velocity, it will have kinetic energy, right? So suppose this is the base and this is a pipe, suppose, and it's at a height. So here it will have potential energy, here it will have potential energy, here it will have potential energy. Since there are different, these are the different heights of the fluid element, these are the different heights. So we'll have a potential energy, and there will be another kind of energy which we call as pressure energy. Yeah, so we'll have another thing called as pressure energy because it's flowing, and for this liquid element it has pressure from the molecules behind it, or like this. Yeah, I already taught you that. Okay, so this has pressure energy, this has pressure energy, it's pushing from behind, so it's flowing like this. So we will consider a pressure energy. So we have kinetic energy, we have potential energy, we have pressure energy. Now let's look at the different energies. So first we will consider the kinetic energy. Kinetic energy. Okay, so kinetic energy of the small fluid element will be how much? It's half mv square. but we will write, sorry, we will write dm into v square. Why dm? Because we are considering this small element, this one, this yellow part, we are considering only this for now. So it will become rho half rho dv v square. Yeah. So if we consider kinetic energy per unit mass, so what will be the formula? Half into v square. And if I consider kinetic energy per unit volume, what will be? Half rho v square. Yeah, am I correct? So this you can write kinetic energy per unit mass. This is kinetic energy per unit volume, right? So next we are going to see, uh, sorry, 1 second, guys. Yeah, sorry for the interruption, guys. So this we can write as kinetic energy per unit. What is it? Mass. Kinetic energy per unit mass, and this is kinetic energy per unit volume. Okay. Next, we'll look at potential energy. Okay. So, what is potential energy? Potential energy, we can write it as U. Capital U denotes potential energy. We can write it for the small element as dm into g into h. We already know potential energy is mgh. So for the small fluid element, we will consider it as dm g h. So with dm, we can write rho dv g h. So now potential energy per unit mass is equal to g into h, and potential energy per unit volume is equal to rho g h. Am I clear? For the mass part, I brought this mass down here, so gh remains, and for this per unit volume part, I brought this dv down to here, so rho g and h. So I got this one. Now we'll see the third type of energy, that is the pressure energy. Okay, so for pressure energy, let's consider a piston here. I'll explain it how it's done. Okay, from here to here, then I draw a piston like this. Okay, then I draw like this, I draw like this, draw like this. Sorry, man. So suppose this is a piston, and I apply force here. Okay, this is the force, so it moves till here. piston moves by a distance of, suppose, small distance dx. Okay, the piston moves by a small distance dx. So what will be the work done? F into dx, right? Now, what we know about pressure? What is pressure? Pressure is force per unit area, right? So this gives us force is equal to pressure into area. Now, if we put this F here in the work done equation, so W is equal to P into A into dx. So what we can write is area of the piston into small distance moved. So what will be this one? This is the displaced volume. You can write it as the displaced volume. So work done is, what is it? This is the energy, right? This is the energy we're talking about. And what energy is this? This is the pressure energy because we applied pressure. That is why this work was being done. So this is the pressure energy. So we can write it here as pressure energy is equal to P dV, right? So now pressure energy per unit mass. What will be P dV by dm? What is volume by mass? You know, so if I bring this dV down, what will be it? It's nothing but density, right? And if we consider pressure energy per unit volume, this is P dV by dV is nothing but P. Okay. Did you get it? So we got three equations, I mean three energies for kinetic energy. We got this is per unit mass, this is per unit volume. So we'll have to see according to the question which one we use, per unit mass or per unit volume. Okay, and this is the potential energy, this is per unit mass, this is per unit volume. And for pressure energy, this is per unit mass, P by rho, and pressure energy per unit volume is P. So now we go to our Bernoulli's equation, right? So let's, here again we have considered a fluid element. Suppose this is a pipe and this is a small mass which is going like this here. Yes, this area is less, this area is more. So we already learned in continuity equation. So let's write the continuity equation here somewhere. Yeah, should we write it? Continuity equation is rho rho1 A1 V1 is equal to rho2 A2 V2. This is the continuity equation. Yeah, so we already learned that. So if the density is same, then it becomes A1 V1 is equal to A2 V2. So here area is less, so velocity will be, area is less, velocity is more, area is more, velocity will be less. So let's look at these 2 points. So what Bernoulli's theorem says, so Bernoulli's theorem states that for steady state laminar flow of non-viscous incompressible liquid for fluid, total energy of the fluid element remains constant. So what did we see? Steady state. These are the assumptions that we take while writing the Bernoulli's equation. Steady state, that means the properties do not change with respect to time. Suppose if I look at this point and I take a watch and I see at 9 a.m. the fluid is flowing at velocity something, say 2 meter per second. I take another reading at 10 o'clock. It still remains 2 meter per second. I take at 11 o'clock. It's still 2 meter per second. So the velocity is not changing with respect to time. So that is called a steady state. So laminar flow, I have already taught laminar and turbulent Reynolds number. Yeah. And non-viscous is what? We consider the viscosity to be zero, or there is no viscosity. Okay. Incompressible means density is equal to constant. So here rho 1 is equal to will be equal to rho 2. So the fluid that is flowing, we consider it to be the same fluid, at the same temperature. The liquid will have constant density. Okay. What is it said? The total energy of the fluid element remains constant. So total energy. So we already found out the three energies. Yeah. So we'll write it for both the points. So we'll write it for both these 2 points. Or first, let me write the equation. So we will write P by rho plus half V square plus GH is equal to constant. Okay. So we have written it per unit in terms of per unit mass. So if I write in terms of per unit volume, P by half rho V square plus rho GH is equal to constant, right? So this is per unit mass and this is per unit volume. Okay. So if we have to write for these 2 points, then we can write it as, do they write the height? Yeah. So this point is at a height of h1, this point is at a height of h2. Okay. So we can write P1 by, I'm writing in terms of mass, okay. P1 by rho 1 plus half, oh sorry, we don't need to write rho 1 because we have taken, what did we take? Incompressible. So the density will be constant. So half P1 by rho is half V square plus, sorry, V1 square plus G into H1 is equal to P2 divided by rho plus half of V2 square plus GH2. So this is my Bernoulli's equation for the 2 points that we saw on the diagram. Yeah, am I clear? So yeah, this is the Bernoulli's equation. So we will solve some numericals, solve some PYQs that have come in the previous years. So do ask me if you have any sort of doubt. We'll take the first few minutes of the next class as a doubt clearing session, and then we will continue with the numericals. And I hope everything will be clear, and I hope you enjoyed today's class. Thank you very much. Have a good day.